1942, Bridgeport, Connecticut. The machine shop floor trembled under the weight of 2,000-pound milling machines as American factory workers hand-scraped cast iron ways to precision measured in 10,000ths of an inch. Through the oil mist and grinding sparks, Bridgeport Series 1 knee mills rolled off production lines built to last generations. No planned obsolescence, no proprietary electronics, no 10-year life cycle limits. Just hand-scraped geometry in meionite cast iron that held accuracy for decades. Modern engineering wisdom says electronics make machines better, faster cycles, tighter tolerances, automated programming that puts human operators to shame. Silicon Valley promises smart manufacturing where software updates improve performance and digital controls eliminate human error. Yet, in 2025, those same high-tech CNC machines sit dead on shop floors, control boards obsolete, support windows closed, retrofit costs exceeding replacement value. While 80-year-old manual mills still cut parts to specification with nothing more than scraped ways and skilled hands. The most decisive engineering contradiction in manufacturing history wasn't written in computer code or programmed into motion controllers, but cast into American iron using principles that made precision rebuildable. Eddie Castellano ran his fingers along the Bridgeport's table, feeling for the telltale roughness that meant another rebuild job. The 1947 Series 1 sat quiet in the corner of H&W Machine Repair, its 2,000-pound mass anchored to the concrete floor like it had grown there. Steam rose from his coffee cup as he flipped the power switch and listened to the spindle motor hum to life, smooth, steady, no vibration telegraphing through the cast iron frame. "Table's been scraped twice since we got her," Eddie called to his apprentice, Marcus, who was wrestling with a dead CNC across the shop. "Still tracks true." He mounted a test indicator to the spindle and swept it across the table's surface. The needle barely flickered, 0.2 variation across 30 inches of travel. Not bad for iron that had been cutting parts when Harry Truman was president. The Bridgeport's column rose from the base in a single casting. Meionite iron poured hot and left to age for months before the first machining cut. No bolted joints to work loose, no separate components to shift out of alignment. Just 8,000 pounds of gray iron with graphite flakes embedded in its crystalline structure, each flake acting as a tiny shock absorber that turned cutting vibration into heat. The ways had been hand-scraped at the factory in Bridgeport, Connecticut, where skilled machinists used blue dye and straight edges to spot high points, then scraped them away with curved tools until the bearing surfaces matched within tenths of an inch. "Eddie, this thing's completely dead." Marcus stood beside the VMC that had arrived yesterday, its control cabinet doors hanging open like a patient on an operating table. "Customer says it just stopped mid-program. Screen went black. Nothing." Eddie walked over and examined the Siemens 840D control system. The display showed nothing but a cursor blinking in the upper left corner. He pulled the main processor board and held it up to the light. Capacitors bulged like tiny beer bellies. Their aluminum electrolytic seals cracked from 15 years of heat cycling. The motion control cards were worse. Their ribbon cable connections corroded green from humidity. "Parts are NLA," Marcus said, reading from his laptop screen. "No longer available. Siemens phased out support last October." Eddie nodded. He had seen this dance before. The machine's mechanical components were solid. Ground ball screws, linear guides, barely worn, spindle bearings tight. 20-ton cast iron frame that could probably cut parts for another 20 years if it had a brain to tell it what to do. But the electronics had aged out of existence. The DOS-based operating system that ran the machine hadn't been supported by Microsoft since 2001. The proprietary motion cards used bus architectures that semiconductor companies stopped manufacturing in 2010. Even the backup battery that maintained the machine's memory was a custom lithium cell that cost $800 when you could find one. "Customers looking at $40,000 for a retrofit," Eddie said, scanning the estimate he had pulled up on his phone. "New CNC control, drives, motors, encoder feedback systems, Or they can buy a new machine for $120,000. What's the machine worth? As scrap? Maybe $5,000. Running? $60,000 on a good day. Marcus shook his head. So they're stuck. Eddie walked back to the Bridgeport and patted its column like an old dog. This girl was built when America still believed in fixing things instead of throwing them away. Look at this parts manual. He pulled a grease-stained book from the shelf, its pages thick with exploded diagrams and part numbers. Every bolt, every bearing, every tiny spring has a number, and Bridgeport kept making those parts for decades. Still can get most of them today from rebuilders and dealers. The manual fell open to a cutaway drawing of the machine's head, each component labeled with military precision: drawbar, quill, step pulleys, spindle bearing retainer. Everything designed to be disassembled, inspected, and rebuilt by a competent machinist with basic tools. No special software, no proprietary diagnostic equipment. No phone calls to Germany to unlock hidden menus. See, they hand-scrape these ways because scraping does something grinding can't, Eddie continued, running his thumb along the oiled surface of the table. Creates tiny oil pockets that hold lubricant. Removes the high spots that cause binding. A good scraper can hold flatness to 1/10 across 3 feet of casting. And when the ways wear, which they will, everything wears, you scrape them again. Restore the geometry, make it accurate again. He gestured toward the dead CNC. That machine has ground ways, hardened to 60 Rockwell. Harder than the scraped ways on this old Bridgeport, more accurate when new. But when they wear, you're looking at a complete machine rebuild, tear down, regrind, reassemble. $20,000 in machine work minimum. And that's assuming the foundry that cast the frame is still in business. Marcus pulled up the machine service history on his tablet. Says here the CNC was installed in 2009. Customer paid $15,000 for the control upgrade in 2017 when the original Fanuc system went obsolete. Now this Siemens is dead, and they're facing another $40,000. 15-year life cycle if you're lucky, Eddie said. I've seen shops where the control dies in 8, capacitors fail, hard drives crash, software gets corrupted, and every generation of CNC uses different communication protocols, different programming languages, different everything. Your operators have to relearn the system every time you upgrade. He cranked the Bridgeport's table handwheel, feeling the smooth resistance of the lead screw threads cut in 1947. This machine has been running the same G-code since Kennedy was president. Same setup procedures, same tooling, same everything. Operator who learned on a Bridgeport in 1960 can walk up to this machine today and be productive in 5 minutes. The apprentice looked skeptical. But the CNC is way more accurate, way faster. You can't compete with a manual machine. Eddie smiled and pulled a gauge block from his toolbox, a piece of hardened steel ground to exactly 1 inch, accurate to within 50 millionths. Want to bet? Rudolph Banno never intended to revolutionize American manufacturing when he started carving patterns in his Chicago basement workshop in 1938. The German immigrant had learned his trade the old way: hand tools, wooden forms, sand casting, but he carried an idea that would outlast every electronic control system invented in the next century. Mass first, then precision. Build it heavy enough to absorb the violence of cutting metal, then machine it accurate enough to hold that precision for decades. The physics hadn't changed since Banno's day, Eddie knew, even as he explained the principle to Marcus beside the old Bridgeport. Cast iron contained flakes of graphite embedded in its crystalline structure like tiny shock absorbers, each flake interrupting the transmission of cutting vibrations through the machine frame. When a milling cutter bit into steel at 1500 RPM, those vibrations tried to shake the entire machine, deflecting the spindle and destroying surface finish. In lightweight machines, those vibrations rang like a tuning fork. In heavy cast iron, they disappeared into heat. Mehanite iron was the secret sauce, Eddie said, tapping the Bridgeport's column with his knuckle and listening to the dead thunk of dense metal. Specialized cast iron with controlled graphite structure. Banno and his partner Magnus Wahlstrom didn't just pour any old iron, they aged it, stress-relieved it, machined it to create a frame that would stay put. The Bridgeport weighed 2,200 pounds stripped down, its column and base cast as a single piece to eliminate joints that could shift over time. No bolted assemblies, no welded fabrications. Just one massive casting that anchored the machine's geometry in iron that would outlast the building that housed it. Marcus ran his hand along the machine's ways, feeling the oil film that clung to the scraped surfaces. Why scrape instead of grinding? Grinding's more accurate. Eddie pulled out his phone and showed Marcus a microscopic image of a scraped surface, tiny peaks and valleys that looked like a mountain range viewed from space. Each one of those little valleys holds oil, hundreds of them per square inch, each one a reservoir that feeds lubricant to the moving parts. A ground surface is smooth as glass, but glass doesn't hold oil. The film breaks down, metal contacts metal, and you get galling and wear. The scraping process itself was an art that connected 19th century craftsmanship to 20th century production. Master scrapers like Richard King, who still taught the trade at Bourne Coke in Illinois, could feel high spots through the scraper handle that measured instruments couldn't detect. They would blue the ways with Prussian blue dye, run a straight edge across the surface, then scrape away the blue spots that indicated contact points. 20 strokes per inch with a curved scraper, checking progress with optical flats and surface plates, working until the bearing surface met engineering drawings that specified flatness within 0.2 of an inch across 3 feet of travel. Bridgeport built over 400,000 of these machines, Eddie continued, opening the parts manual to a page showing exploded diagrams of the spindle assembly. Every single one documented like a Swiss watch. Part numbers, torque specifications, bearing clearances, oil capacities. They expected these machines to be rebuilt, not scrapped. The manual showed spindle bearings available in multiple classes of precision, replacement gears for the step pulley transmission, even the tiny ball oilers that fed cutting fluid to the ways. Everything engineered for disassembly and renewal. Modern CNC builders operated under different assumptions. Planned obsolescence wasn't malicious. It was economic reality in a world where Moore's law made computer processors twice as fast every 18 months. Why engineer a control system to last 30 years when the hardware would be laughably obsolete in 5? Better to design for the replacement cycle, upgrade paths that kept customers buying new capabilities as technology advanced. But the iron didn't follow Moore's law. Cast iron from 1947 performed exactly the same as cast iron from 2025, governed by physics that hadn't changed since Newton. Marcus pulled up specifications on his tablet for a modern Haas VF2 machining center. Says here this new machine has a 40 horsepower spindle, 24-tool automatic changer, rapids at 1,500 inches per minute. The old Bridgeport has what, 2 horsepower? 1.5, Eddie corrected, but look at the frame construction. He showed Marcus a cutaway drawing of the Haas, a welded steel frame filled with concrete for damping, aluminum components to save weight, linear guides instead of traditional ways. Lighter, faster, more complex. Built to run lights out with minimal operator intervention. But when something breaks, you're calling the service hotline and waiting for a technician with a laptop full of diagnostic software. The density difference told the story in numbers that Banno had understood instinctively. Cast iron weighed 7.2 grams per cubic centimeter. Aluminum weighed 2.7. Steel fell somewhere between, but steel fabrications used hollow sections and ribs to minimize weight while maximizing stiffness. The old Bridgeport's column was solid iron 3 inches thick. A modern machine center might weigh the same overall but distributed that mass across aluminum housings, steel framework, and concrete damping compound. When cutting forces tried to deflect the structure, mass concentrated at the cutting point provided the best resistance. The old guys built heavy because heavy works, Eddie said, gesturing toward a South Bend lathe from 1949 that occupied another corner of the shop. John O'Brien's company made nearly half the engine lathes in America by 1930, sold them to trade schools, small shops, big factories. Everyone built like a locomotive, cast iron beds 12 inches thick, lead screw assemblies that weighed more than some complete modern lathes. The South Bend's bed showed the same hand-scraped way construction as the Bridgeport, but scaled for turning operations that required absolute rigidity between headstock and tailstock. O'Brien had understood that accuracy wasn't just about tight tolerances in manufacturing, it was about maintaining those tolerances over decades of use. The lathes' ways were flame-hardened and hand-scraped to create bearing surfaces that could be restored to original specification after years of wear. Parts manuals from South Bend Lathe Works listed every component down to the smallest washer, with factory service departments that kept obsolete parts in stock for machines built before the Depression. That's why these old machines keep running, Eddie concluded, patting the Bridgeport's solid flank. They were designed by people who expected to fix them. Georg Schlesinger had never set foot in a Chicago machine shop when he published his acceptance tests in 1927, but his influence shaped every precision machine that followed. The German engineer's systematic approach to measuring accuracy, checking spindle runout, verifying perpendicularity between axes, testing straightness across travel, created a universal language that connected builders and buyers across continents and decades. When Eddie pulled his test indicator across the Bridgeport's table, he was following procedures that Schlesinger had codified almost a century earlier. Geometry lives in the iron, Eddie explained to Marcus, mounting a precision square against the machine's column and checking it with the indicator. Everything else is just convenience. The needle held steady as he swept the indicator along the square's edge, no deviation across 12 inches of travel. The column's perpendicularity to the table had been established when the machine was new through careful scraping of the ways, creating reference surfaces that would define the machine's accuracy for its entire working life. The scraping process itself embodied a philosophy that modern manufacturing had largely abandoned. Richard King, who still taught the craft at machine rebuilding shops across the Midwest, could restore geometry that had been lost to decades of wear and neglect. His students learned to read bearing contact patterns like topographical maps, identifying high spots that needed attention and low areas that required shimming or selective scraping. 20 points of contact per square inch was the standard, enough to distribute loads evenly while maintaining the oil pockets that prevented galling. "Watch this," Eddie said, applying a thin coat of Prussian blue to a precision straight edge. He ran the blued edge across a section of the Bridgeport's table, leaving marks that revealed the contact pattern beneath. The blue spots formed a random constellation across the scraped surface, each mark indicating a high point where the straight edge had touched the iron. A properly scraped surface showed even distribution of these contact points, proof that loads would spread uniformly across the bearing area. The alternative approach, grinding the ways to perfect smoothness, looked more precise on paper, but failed in practice. Ground surfaces, mirror smooth and geometrically perfect, couldn't retain the oil films that prevented wear. Without the microscopic valleys that scraped surfaces provided, lubricant squeezed out under load, allowing metal-to-metal contact that destroyed accuracy over time. The old craftsman had understood this intuitively, creating surfaces that looked rough under magnification but performed flawlessly under the demands of production cutting. Marcus examined the blued straight edge, noting how the contact pattern revealed minute variations invisible to the naked eye. "So you scrape away these high spots?" "Exactly, but you have to know when to stop." Eddie demonstrated with a sharp scraper, removing a few thousandths of material with careful, controlled strokes. Too much scraping and you create low spots. Not enough and the bearing loads concentrate on the high areas. It takes years to develop the feel. The rebuilding process required more than skilled handwork. It demanded understanding of the machine's original specifications and the ability to restore them without modern factory tooling. Shops like H&W Machine Repair kept surface plates accurate to micro-inches, optical flats that revealed straightness deviations measured in wavelengths of light, and master straight edges ground to laboratory standards. These reference tools allowed rebuilders to check their work against the same standards Bridgeport had used in 1947. Frederick Geyer at Cincinnati Milling Machine had institutionalized this approach to accuracy during the golden age of American machine tools. His company's research department studied metal cutting like a science, measuring chip formation, analyzing cutting forces, documenting the relationship between machine rigidity and surface finish. Cincinnati mills earned reputations for holding tight tolerances not because they were built to impossibly precise standards, but because their geometry remained stable under cutting loads. Geyer understood that a machine accurate to a tenth of an inch in the showroom was worthless if it deflected several tenths under the stress of heavy cutting. "That's why the old documentation matters so much," Eddie said, pulling out a Cincinnati Milling Machine manual from 1952. The pages detailed acceptance tests that buyers could perform to verify their machine's accuracy, run-out checks, alignment procedures, straightness measurements across the full travel of each axis. They expected customers to verify the geometry and restore it when necessary. Modern machines come with warranties instead of restoration procedures. The philosophy extended beyond individual components to the entire machine's architecture. Bridgeport's engineers had positioned the spindle, column, knee, and table to minimize deflection under cutting forces, creating a structure that maintained accuracy even when removing heavy stock. The knee's dovetail ways supported cutting loads through the full depth of the casting, not just at surface contact points. The column's mass resisted the overturning moments created by long-end mills working at the edge of the table. Every element reinforced the machine's fundamental stability. Marcus studied the manual's geometric diagrams, noting how each measurement built on the previous ones. "It's like a pyramid. Everything depends on the base being right." "The base and the ways," Eddie agreed. "Get those wrong, and nothing else matters. Get them right, and the machine will cut accurately for generations." He showed Marcus photographs from rebuilding operations where craftsmen had restored 40-year-old machines to better than new specifications. Column ways reground and scraped to hold 2/10 flatness. Spindle assemblies rebuilt with modern bearings and tighter clearances. Knee and saddle ways remachined to eliminate wear and backlash. The economic logic was inescapable for shops willing to invest in restoration rather than replacement. A complete rebuild of the Bridgeport, new bearings, scraped ways, rebuilt spindle, cost perhaps $8,000 and returned a machine capable of holding tolerances that matched current production equipment. The same $8,000 might buy a down payment on a new CNC system that would require obsolescence planning within a decade. "The iron doesn't wear out," Eddie concluded, running his hand along the machine's solid flank. "It just needs attention. And the geometry, once you establish it properly, wants to stay put. That's what Schlesinger figured out. Measure it right, document it completely, and you can bring it back whenever it's needed." The notification arrived in shop inboxes across America on October 1st, 2024, with the sterile efficiency that marked the end of technological eras. Siemens Product Lifecycle Management announced that Sinumeric 840DSL CNC controls had entered phase-out status, effective immediately. Spare parts availability would continue for 5 years, then taper to 0. Technical support would migrate to newer platforms. Upgrade paths were available for customers willing to invest in current generation hardware. The language was diplomatic, professional, and final. Marcus pulled up the announcement on his tablet, scrolling through pages of model numbers and transition schedules. "Says here they're focusing resources on the new 840DSL Edge platform, better connectivity, improved user interface, enhanced cybersecurity features." He looked up from the screen. "Makes the old system sound like it's from the Stone Age." Eddie examined the control cabinet of the dead VMC, its Siemens badges still bright after 15 years of faithful service. The machine had been cutting parts just hours before its electronic brain suffered what technicians called a catastrophic failure, multiple component failures cascading through interconnected systems until nothing worked. The main processor board showed obvious signs of capacitor failure, those critical aluminum electrolytic components that stored and released electrical energy thousands of times per second. After 15 years of heat cycling, their internal chemistry had degraded past the point of reliable operation. "Capacitors are the weak link in every electronic system," Eddie explained, holding up one of the failed components. "These aluminum electrolytics are rated for maybe 10,000 hours at 85 degrees Celsius. Sounds like a lot until you realize that's less than 2 years of continuous operation. Cool them down 10 degrees and they last twice as long. but stick them in a control cabinet with heat-generating drives and processors, and they're on borrowed time from day one. The mathematics of electronic obsolescence followed predictable patterns that shop owners had learned to accept as the cost of modern manufacturing. Control systems typically lasted 8 to 15 years before component failures, software incompatibilities, or vendor phase-outs forced replacement decisions. Motion control cards used communication buses that semiconductor manufacturers discontinued in favor of newer standards. Operating systems evolved beyond the capabilities of embedded hardware. Even backup batteries used proprietary chemistry that became unavailable when suppliers consolidated or exited markets. Marcus traced the connections between the failed control and the machine's mechanical systems, servo motors, encoders, coolant pumps, spindle drive. All this mechanical stuff looks fine. It's just the brain that's dead. That's the contradiction, Eddie said. The part that wears out is the part that's supposed to be improving. He pulled up industry statistics on his phone, showing the steady march of electronic evolution that drove obsolescence cycles. Processor speeds doubled every 18 months, following Moore's law with relentless precision. Memory capacities expanded exponentially. Communication protocols evolved from serial interfaces to Ethernet to wireless systems that hadn't existed when the machine was installed. The dead CNC represented millions of dollars in similar equipment across American manufacturing, sophisticated machining centers, turning centers, grinding machines, and fabrication equipment rendered inoperable by electronic failures in systems that were otherwise mechanically sound. A modern Mazak 5-axis machining center might cost $400,000 new, but become worthless overnight when its control system failed and replacement parts were no longer available. The mechanical components, ball screws, linear guides, spindle bearings, structural castings, often retained 90% of their useful life when the electronics died. "Look at this repair estimate," Marcus said, showing Eddie a quote he had received from an authorized service center. $42,000 for a control retrofit. New CNC, new drives, new operator interface, new everything, plus 2 weeks downtime while they install and debug the system. Eddie nodded grimly. The retrofit market had become a substantial business as shops faced the reality of electronic obsolescence. Companies like Centroid, Fagor, and Heidenhain offered retrofit packages that promised to restore dead machines to productive operation, often with capabilities that exceeded the original equipment. But the economics remained brutal, investing nearly as much in a retrofit as the machine was worth, with no guarantee that the new control wouldn't face its own obsolescence cycle in another decade. The alternative was replacement, which created its own challenges. Modern machining centers delivered impressive capabilities, faster spindle speeds, higher accuracy, better surface finishes, automated tool changing, adaptive control systems that optimized cutting parameters in real time. But they also represented complete dependence on electronic systems that were guaranteed to become obsolete. A shop that bought a new CNC in 2025 was essentially purchasing a 10-year lease on productivity, after which they would face the same obsolescence decisions all over again. Fanuc does it differently, Eddie said, pulling up the Japanese company's service philosophy on his phone. They advertise lifetime maintenance support, keep making parts, providing service, updating software, proves it can be done if the business model supports it. The Fanuc approach stood as proof that electronic obsolescence wasn't inevitable, it was a choice. Their control systems remained serviceable for decades, with spare parts availability and technical support that outlasted multiple generations of competing products. But Fanuc represented the exception rather than the rule in an industry where quarterly earnings reports rewarded new product introductions over long-term support commitments. Marcus examined the dead control cabinet, noting the manufacturing dates on various components. Processor board from 2008, motion cards from 2009. Some of these components are older than I am. And they worked perfectly until yesterday, Eddie replied. That's 15 years of reliable operation, 3 shifts a day, making parts and making money. The only reason this machine is dead is because we can't get a $70 capacitor and a $200 processor board. The irony wasn't lost on either of them. The mechanical systems that surrounded the failed control, spindle assemblies, axis drives, structural castings, represented 19th century engineering principles refined through decades of incremental improvement. Cast iron, steel, bronze, materials that followed physical laws, unchanged since Newton. But the electronic systems that controlled those mechanical components operated in a different universe, governed by Moore's law and market forces that demanded constant obsolescence and renewal. So what happens to the machine? Marcus asked. Eddie looked at the massive casting that formed the machine's structure, easily capable of another 20 years of productive service if it had a functioning control system. Depends on what the customer decides: retrofit, replace, or scrap. None of the options are good. Eddie positioned the gauge block on the Bridgeport's table with the deliberate care of a surgeon placing an instrument. The hardened steel cube measured exactly 1 inch in all dimensions, ground and lapped to an accuracy of plus or minus 25 millionths of an inch, a precision standard that had remained unchanged since the National Bureau of Standards established dimensional references in the 1920s. Marcus watched as Eddie selected a 2-inch face mill, its carbide inserts sharp enough to shave the hair from his forearm. Light cuts and patience, Eddie said, adjusting the machine's step pulley to its lowest speed. That's how you coax accuracy from manual equipment. He positioned the cutter above the gauge block, cranking the knee upward in increments measured in thousandths. The Bridgeport's hand wheels bore graduation marks that allowed positioning to half a thousandth, but Eddie relied on the machine's inherent feel rather than scale readings. Decades of experience had taught him to sense when cutting forces were building, when the spindle was deflecting, when the setup was fighting him instead of cooperating. The first pass removed a whisper of material, aluminum-colored chips curling away from the carbide teeth as they swept across the hardened steel surface. Eddie fed the table by hand, maintaining constant pressure against the lead screw backlash while monitoring the cut through sound and vibration. No electronic feedback, no adaptive control algorithms, just human senses interpreting the mechanical symphony of metal cutting metal. The surface finish emerged mirror bright, unmarred by chatter marks or tool deflection. "Check it," Eddie said, handing Marcus a precision square and a set of gauge blocks. The apprentice stacked blocks to create a 1-inch reference, then compared it to the freshly machined surface. The indicator needle barely moved, 5/10,000ths deviation across the entire face. Not the precision of a coordinate measuring machine, but well within the tolerances that most production parts required. Across the shop floor, the retrofitted VMC hummed to life under the control of its new Centroid CNC system. The machine's original mechanical components, ball screws, linear guides, spindle assembly, remained unchanged, but a modern control cabinet now housed contemporary electronics designed for 21st century manufacturing demands. Touchscreen interface, Ethernet connectivity, USB program storage, all mounted on the same cast iron frame that had supported the original Siemens system. Customer approved the retrofit, Eddie explained as the VMC's spindle accelerated to 8,000 RPM. $42,000 to give this machine another 15 years of productive life. The new control system spoke the same G-code language as its predecessor, but with processing power that dwarfed the original electronics. Programs that once required minutes to load now executed instantaneously. Tool changes that had taken 30 seconds now completed in 12. Marcus programmed a simple facing operation, watching as the machine positioned itself with servo-driven precision. The spindle plunged into the same gauge block that Eddie had machined manually, removing material in a controlled spiral that left a surface finish measured in micro-inches. When the cycle completed, the part measured within 2/10,000ths across its entire surface, marginally better than the manual machine, but achieved in 1/10 the time. Speed versus skill, Eddie observed, comparing the two finished surfaces under magnification. Both met engineering requirements. Both demonstrated the fundamental capability of their respective approaches. The manual machine required operator expertise to achieve accuracy, while the CNC delivered precision through automated control systems. But both depended on the same physical principles: rigid structures, accurate spindles, precise motion control that had defined machine tool design since the Industrial Revolution. The economic comparison revealed the complexity of modern manufacturing decisions. The Bridgeport consumed 15 minutes of skilled labor to machine the gauge block, while the retrofitted VMC completed the same operation in 90 seconds of largely unattended cutting. For high-volume production, the productivity advantage clearly favored automated equipment, but the Bridgeport would continue operating long after the retrofit control became obsolete, requiring only basic maintenance and operator skill to remain productive. "Here's what really matters," Eddie said, pulling up cost analyses on his tablet. "That retrofit gives the customer maybe 15 years before they face the same obsolescence cycle again. New controls, new software, new everything. The iron stays the same, but the electronics keep aging out." He showed Marcus projections that extended the analysis forward. Another retrofit in 2040, then 2055, each upgrade costing more than the previous as complexity increased and support options narrowed. The Bridgeport's economics followed different mathematics. Annual maintenance costs remained essentially constant: way oil, spindle bearings, an occasional gear replacement. Major rebuilding every 20 to 30 years, restoring the machine to better-than-new condition through scraping and mechanical refurbishment. No planned obsolescence, no forced upgrades, no compatibility issues with future software releases. Just iron, steel, and bronze components that followed physical laws unchanged since Archimedes. Marcus examined both machines, noting how their fundamental architectures remained remarkably similar despite 7 decades of technological evolution. Cast iron frames provided structural stability. Precision spindles delivered cutting accuracy. Controlled motion systems positioned workpieces and tools. The retrofitted VMC achieved these functions through electronic sophistication, while the Bridgeport relied on mechanical elegance, but both machines served the same essential purpose: removing material with predictable accuracy. "The iron didn't last 80 years by accident," Eddie concluded, his words carrying the weight of accumulated wisdom. "Banau, Wallstrom, O'Brien, all those old builders, they designed these machines to be fixed. Mass for stability, scraping for accuracy, documentation for service. They built an ecosystem where parts and knowledge stayed available for decades. The proof-cut results spoke with mathematical certainty. Manual skill could coax precision from mechanical systems that predated electronic controls by generations. Modern CNC delivered speed and repeatability through computational power that would have seemed magical to the original builders. But both approaches depended on the same fundamental insight: that accuracy lived in the geometric relationships between machine components, not in the sophistication of the control systems that directed their motion. If we pair that old American habit with smarter, supportable controls," Eddie said, gesturing toward the successfully retrofitted machine, "our equipment doesn't die in 10 years. It runs as long as we keep faith with maintenance and with each other." The machines stood side by side, separated by 7 decades of technological evolution, but united by their commitment to the ancient craft of making things precisely. One represented heritage maintained through skilled hands and mechanical understanding. The other embodied heritage renewed through electronic sophistication, married to proven mechanical principles. Both would continue cutting metal long after their contemporary competitors had been scrapped for obsolescence.